Hi, everyone. On behalf of Dr. Farshid Torabi at the University of Regina, I'm hereby presenting a presentation titled Foamy Oil Formation and Stability through Utilization of Microfluidics. And today, the presentation outline is divided into several sections, including introduction and motivation, experimental materials, setup and procedures, results and discussion. Also, we will briefly talk about the future direction of microfluidic studies on non-equilibrium phase behavior. Also, the big data analytics on flow optimization for post-chop COR techniques. And then we'll jump to the conclusions and recommendations. For solvent dissolution and exsolution mechanisms, as well as foamy oil formation and stability study, traditional methodologies usually include traditional PVT cell, transfer cylinder, core, flood, and sandpacked models, as well as CT scanning type of methods. Though these methods have been widely used, inevitably, they have their shortcomings, such as low visual accuracy, non-visualization, as well as expensive and highly equipment dependent. Therefore, in this slide, we show that the foamy oil formation and stability study that was conducted by the scholars in the past. But here we can see it is only a qualitative characterization of foamy oil instead of a quantification of foamy oil. And hence, motivated by this, we have applied microfluidic system to study foamy oil phenomena. In order to observe real-time foamy oil kinetics, Dr. Farshid Torabi's research group has utilized microfluidic-based platform as an important complementary measure to the traditional methods. There are three types of micromodel we commonly use in the lab, including nano to micrometer, medium pressure, high temperature reservoir chip, micro to millimeter scale micromodel for highly viscous fluid study, as well as a fully customizable glass micromodel contained in a high pressure, high temperature chamber for extensive operating conditions study, including multiple pressure, temperature, and various test fluid types and components. And our main target is to upscale the microfluidic experimental results to a laboratory scale results so that we can use it to update to upscale to a future to a field scale in the future for its practicability. Our main research interest is the two main solvent injection mechanisms shown here as solvent dissolution and solvent exsolution. Solvent dissolution mainly include pressure decay tests in a closed thermodynamic system under various temperature. And solvent exsolution mainly operates as pressure depletion at specified rates and steps under various temperature. These are the two schematics of dissolution and exsolution. And foamy oil mainly occurs in the solvent exsolution processes. And that is also our main interest. The materials that we use in our study is a heavy oil sample that was mixed by kerosene to bring down the original viscosity at 132,000 centipoints to 1,500 centipoints. And the solvent is a pure carbon dioxide and a mixture of CO2 and C3. The purpose of bringing down the viscosity is trying to prove the feasibility of foamy oil formation and stability study in such microfluidic system. And if it works, the viscosity of the oil sample will be brought up step by step to a very high level. An experimental setup, we have live oil recombination and differential liberation test unit. We have a bulk phase visual cell unit, as well as a porous media glass micromodel unit. And the study procedures mainly include live oil differential liberation tests for equilibrium thermodynamic properties, solvent dissolution and exsolution tests in bulk phase and porous media systems. And then we will do automatic image processing and data quantification from the achieved large photo sets. And also last, the experimental data will be history matched and relevant numerical parameters will be quantified by a MATLAB controlled reservoir simulator with a real-time optimization module. And resultant discussion. Our main target, as we said, is to upscale the kinetics of non-equilibrium interface mass transfer into a lab scale or even a field scale. So here is direction. First is the single bubble exsolution tests at a micro scale compared with the CCE test in a lab scale, as well as a single bubble dissolution tests compared with a solvent dissolution tests in the lab scale to see their relationship. First is the solvent exsolution in the bulk phase visual cell tests. CCE tests were conducted in such a setup. And here is a GIF showing a dynamic bubble kinetics, and we can have a look for several seconds to see the histogram as well as the corresponding picture that we achieved in our bulk phase visual cell. Okay, so here is a brief introduction of the results for the bulk phase visual cell CCE tests. Two most important parameters we achieve is the total liquid phase volume fraction in the closed system, as well as the non-equilibrium K value that is calculated based upon this total liquid phase volume fraction in the closed system. And these two parameters will be used mainly for the history matching, and they will be history matched as the main target. And here is the two tests we extracted out of all the CCE tests as a representative for the subsequent numerical simulation. And for one is the minus 20 kPa half saturated visual cell test, and the other is a minus 20 kPa per minute of fully saturated visual cell tests. On the left-hand side is the total liquid phase volume fraction difference between the experimental state and the equilibrium state that was calculated based upon equation of state. And on the right-hand side is the K value comparison. And as we can see, the red curve on the right-hand side means the equilibrium K value, and the black dots represents the non-equilibrium value. You can see there is a gap between the non-equilibrium and the equilibrium value, which indicates a delayed solvent exsolution. Also, based upon the liquid phase fraction, as well as the non-equilibrium K value, we have applied numerical simulation in a continuum scale simulator. coupled with the MATLAB optimization module. On the left-hand side, we can see if equilibrium K value is applied, that the experimental results will have a gap between non-equilibrium data and the equilibrium data. But when the non-equilibrium K value was applied in the simulation, we can see that the history match was finished, and you can see the curve was history matched. And here is the non-equilibrium K value that was achieved from the numerical simulation. And also we can see there is a gap between equilibrium K value as well as the non-equilibrium K value. And by combining a CO2 and C3 H8 as one pseudo component, we can see that the non-equilibrium K value of the mixture solvent lies between individual solvents' non-equilibrium K value. And here, we have conducted another type of test, which is a single bubble X solution test. By creating a nucleation site in our micro channel, we can have the bubbles nucleated from this nucleation site and then grow. Here is a GIF for showing how the bubble grows in our nucleation site. And this nucleation depth or length is 850 micrometer. And also we have conducted another type of, we use the CMOST optimization module to history match our experiments as well. And it was found that by using the solvent bubble, single bubble X solution test results, we have also yielded similar history matched curves as just like we have used the MATLAB controlled reservoir simulator. And by upscaling, we have figured out that the optimized reaction kinetic rate of bubble X solution was similar to the reaction to the exclusion kinetic factor that have been achieved through single bubble X solution tests. Here we have conducted a solvent X solution tests in a porous media glass micro model instead of a bulk phase visual cell. As we can see that the live oil was saturated in the micro model, and then the live oil was underwent a pressure depletion process to generate gas bubbles. In this figure, we can see same as the bulk visual cell test, there is a gap between the vapor phase volume fraction between the non-equilibrium condition as well as the equilibrium condition. And on this left-hand side is that we can see that the gas phase is gradually exhausted from the oil and accounts for more and more space in the micro model. And this finding is similar to the study conducted by Sadney et al. In 2004. Also, another type of solvent static CCE tests were conducted. And as we can see, by applying a fixed pressure depletion rate, also a non-equilibrium vapor phase volume fraction and equilibrium vapor phase volume fraction was observed. In another test conducted by the porous media glass micromodel is called the continuously convective flowing test. And we have utilized the micromodel system to pass the foamy oil through the micromodel in order to observe different bubble textures under pressure depletion. Here is the two different bubble textures that we have observed during the pressure depletion. On the left-hand side is very tiny, and the bubble density is very dense. And on the left-hand side is a relatively larger bubbles observed in the micromodel during the foamy oil flow. Okay. This figure quantifies the vapor phase volume fraction in the micromodel, as we can see by applying a continuously convective condition, that is a forced convection. We have a very stabilized vapor phase volume fraction. This is mainly due to the continuous shredding of the bubbles, and also which makes the larger bubbles become smaller bubble, and the smaller bubble will redissolve into the bulk phase liquid under Oswald ripening mechanism. And hence, that in the liquid phase, there is excessive mass of solution gas, which use the non-equilibrium condition. In here, we have another solvent dissolution test, is the single bubble dissolution tests. And then by applying the single bubble dissolution, we can achieve the single bubble dissolution rate that could be history matched, also as well as a reference to the pressure decay tests we have conducted in the micromodel. Here is a GIF of how the foamy oil was created before the system was repressurized into high pressure to conduct the solvent dissolution tests. You can see that the bubbles were nucleated intensively from the nucleation side and form multiple smaller bubbles as a foamy texture. And by tracking one of the bubble, we can see how it redissolves when the system was repressurized. The second type of bubble is a Taylor bubble, and by presaturating a column of gas in the micro channel, and then by pressurizing it to a designated pressure, we can see that the bubble is gradually redissolved into the liquid surrounding it. So this Taylor bubble and spherical bubble is the main target that we're using to study solvent dissolution techniques, solvent dissolution kinetics. And here is the results and discussion. By extracting the bubble volume in a real-time basis, we have extracted the bubble dissolution kinetic rate on a dimension of time to the power of -1, which is suitable for incorporating into a reservoir simulator. And here is the extracted bubble dissolution rate. So by knowing the bubble dissolution rate, we want to upscale to see if this bubble dissolution rate can be used in a pressure decay method conducted in a relatively larger scale. Therefore, using the micromodel, we are conducting a pressure decay test by pressurization of the solvent and then let it soak into the oil phase. And by using the micromodel as a micro PVD cell, we have used pressure decay curve for several sets. And as we can see that every at the end of each pressure depletion, at the end of each pressure decay tests, the solvent mole fraction in the live oil is approaching equilibrium value. When the model was positioned perpendicular to the ground, we can also see that the solvent mole fraction in live oil was approaching equilibrium. So in order to simulate this bubble dissolution, we have applied two boundary conditions. One is a quasi-equilibrium boundary condition. The other is a non-equilibrium boundary condition. And here is an example of the trial and error of the history of the pressure decay curve matching. And here is the final result. And also by utilization of computational fluid dynamics, we can calculate the intrinsic permeability of the micromodel section that we choose to conduct pressure decay tests. And we can fit this permeability into a continuum scale reservoir simulator. Therefore, first, by a quasi-equilibrium interface condition, which is a EOS-based method, the effective diffusion or dispersion coefficient adjustment is the main parameter we adjust to account for pressure decay. As we can see that for a vertical condition and for a horizontal condition, we can see that the vertical test always use a relative higher effective diffusion coefficient due to the gravitational force, which facilitates oil to flow down and expose deeper oil to be diffused by solvent. And another interface condition is the non-equilibrium interface condition, which is a kinetics-based. By extracting the bubble dissolution rate from the Taylor bubble test, we first use a CMOST to history match the pressure decay curve, and then we have yielded a pretty good result. And then we have also used a MATLAB control, a coupled reservoir simulator by a refined time stepping method to yield an even better history matching results. And in a kinetic-based model, the kinetic rate reaction frequency factor adjustment is the main parameter we account for a solvent condensation and pressure decay. And here is the comparison between the kinetic dissolution rate of a Taylor bubble and the kinetic dissolution rate of the pressure decay test. As we can see that the yellow dots are the Taylor bubble kinetic rate, and the little circle are the optimized kinetic reaction rate that are achieved through history matching. And we can see that the dissolution rate of solvent in the micro model is very similar to the Taylor bubble, but they are relatively slower because a Taylor bubble has a larger contact area between the bubble and the liquid surrounding them. But for a pressure decay test of solvent and micro model, they have a relatively smaller contact area. But the order of magnitude between the Taylor bubble dissolution rate and the bulk phase pressure decay dissolution rate are very similar. And here is a brief introduction of the flooding and CSI tests we have conducted in our micromodel system. And we can see under different capillary number, we have different viscous fingering phenomena. And also we have tested the reproducibility of viscous fingering at the same capillary number, and we can see that the reproducibility was pretty good. So here, we want to briefly talk about the future direction of what microfluidic platform can do on foamy oil formation and stability study. The first is that we can do a two-phase CCE tests, which exclude the aqueous phase in the reservoir. And also we can use mixture solvent like carbon dioxide, methane, and propane, as well as heavy oil. And the second is a three-phase CCE tests, which includes mixture solvent, heavy oil, as well as the aqueous phase, which include polymer, alkaline, surfactant, nanoparticles, as well as any chemicals that has reaction with the in situ water. And also we can do the residue oil droplet remobilization tests to reactivate the non-oil producing formations or the suspended wellbores. And also, the last but not least is to conduct a blockage test in high permeability zone in a post-shock reservoir. This helps to prevent either gas or water breakthrough and will lead to a higher production of oil phase. And also, a big data analytics and machine learning on foamy oil on flow optimization for post-shock reservoir will also be conducted based upon the vast resources on the internet, also the vast data set from all kinds of literatures. And we can establish an experimental study database as well as the numerical study base database to screen out the essential parameters that optimize a CO2-based solvent injection processes. And you can take a look at this introduction in this description here. So last part is the conclusion and recommendation. For conclusions, we have conducted the CCE tests compared with a single bubble X solution test. And we have found that the non-equilibrium phase volume fraction of the system was quantified and compared with the equilibrium state to identify the non-equilibrium regime of solvent at solution. Also, a transient K-value methodology can be used to history match the non-equilibrium vapor volume fraction of a thermodynamic system undergoing pressure depletion tests. And also we have conducted the kinetic-based modeling by inputting the pressure and bubble X solution rate relationship achieved in the single bubble X solution tests in a continuum scaled reservoir simulator, and we have achieved pretty good history matching results. And the solvent dissolution and exsolution tests, mainly the dissolution here, was compared with a single bubble dissolution test. And we have found that by using the two different interface conditions, or we call the boundary conditions, which is the quasi-equilibrium and a non-equilibrium condition, the effective diffusion coefficient and was tuned to history matching the pressure decaying results in a quasi-equilibrium condition. And for the non-equilibrium interface condition, the kinetic rate of solvent condensation into oil was tuned to history match the pressure decay curves. And we've also found that the order of magnitude of the optimized kinetic rates were close to the Taylor bubble dissolution rate, which indicates a kind of a direct upscaling of dissolution behavior from a micro scale to a lab scale. And last is the recommendations. Is the recommendation of what we can do in the microfluidic platform. We can apply a wider range of pressure and temperature to study non-equilibrium dissolution and exsolution behavior. Also, we can also have multiple components. And third is that if possible, we can make a movable and a chemically stable liquid piston which withstands high pressure and high temperature in a microfluidic device to create a closed system. Fourth is the reservoir complexity can also be applied in a microfluidic system by using various different micropatterns. And last is the real-time concentration field measurement can be developed to accurately determine the mass transfer profile, especially for non-parent, thicker, and heavy crude oil samples. Here are the references that we used in our study in this presentation. And the acknowledgements to University of Regina, to PTRC, to CNRL, to Cenovus and Husky Energy, and also to Mitex and CNG for the simulation software license. Thank you very much.